Good evening. Today we're going to stream a heavy met talk, one of the first actually, this is a third, from an empty studio at Klimahuset in Oslo due to the corona outbreak. And I'll talk about a new reason for why we should expect to see more extremely high precipitation amounts. This research was motivated by the need to explain why we can expect more extreme rainfall when we get global warming. And obviously, the obvious explanation that higher temperatures give higher rates of evaporation and more moisture in the atmosphere is one reason. But the question is that the whole story? No. Because we know that the clouds have got higher cloud tops. And the higher cloud tops implies more intense rainfall because the cloud drops have a longer distance to fall before they reach the surface. And by that time, they can actually collect more moisture on the way down, so you get more intense rainfall. So, are there more factors than these two? And then, I usually cycle to work in the summer, 1 hour each way, so 2 hours in total every day. And I normally don't get soaked by rain when I cycle to work. Whereas when I cycle past the Oslo fjord, I know evaporation is going on all the time, continuously. There's always evaporation. So basically, what is evaporated, the water vapor has to come down, so what comes up goes down. And it doesn't rain everywhere and all the time. The rain comes in patches, in time and space. So basically what goes up has to come down in a different area. So then I thought, maybe look at the area of rainfall. What is the area of rainfall in the world? Because you have to force all the water into like a little area. So then I thought, okay, how do I find the global area of rainfall? And then I thought, well, we have the satellites, right? This is a satellite picture showing the clouds and the surface. It's not perfect, the satellite data is not perfect, but it's very useful information. And there are also other type of radar data for rainfall, not just the visual picture. And here's one figure showing the area of rainfall, or where it rains on a random day. So the blue areas here show where it rains on a random day, and the whites are where it doesn't rain. So this is a typical rainfall picture. And this data is based on the Tropical Rain Measurement Mission, or called TRMM in sort of cryptic speak. And this data covers 50 north to 50 south, and that represents 77% of the Earth's total surface, and also where most of the action takes place when it comes to the hydrological cycle. And then from this type of picture, we can say that it rains typically on 25% of the area in the world. And if we assume that evaporation takes place over all oceans because you have wet surfaces, so that represents, say, 70% of the Earth's surface. So then you have a ratio of 1 to 3. So if it on average evaporates 1 millimeter per day in all oceans, then you will get on average 3 millimeters per day in the places where it rains. And this is some kind of a funnel effect. So you sort of squeeze everything into a smaller area. And basically the mean intensity of rainfall is proportional to the area of evaporation divided by the area of rainfall. Then because this data starts in 1998, and there's a measurement every day since then. And I thought, okay, so what does it look, does this area change over time? So I could plot the each day I could plot the area. So that's the red curve here, and the black curve is a trend line here. So basically, in 1998, it typically rained on 25% of the area. By the end of my analysis in 2016, 23%. That means, like, in a relative sense, it's a 7% decrease over 2 decades. And that is actually quite profound and also quite serious, because that means that you get more rain concentrated where it rains, and then it takes longer time between each time it rains, at least in certain regions. So the implications is that you get more floods and more droughts. So this is like, I looked at 2 different data sets, and then I thought, okay, what if we look at other types of data sets? Can we actually see the same picture there? So of course we have the rain gauge data. They have daily rain amounts, but the rain gauge data is not really global. It sort of gives us some snapshots in different places, but they're not really global. But what we saw was that we can look at the mean rainfall amount only on the days when it rains. And then if we look at how often it rains, then we can actually explain how often we get heavy rainfall. And this one figure here shows one example. So the red curve shows the number of days per year with more than 10 millimeters in Oslo. And the black curve shows the estimated number of heavy rain days based, given the wet day mean precipitation, that's the mean intensity, and the wet day frequency. And you see that these actually do tend to follow each other quite well. So the calculations are on the black curve here. So that shows that basically when you get more, like on average, more when it rains, you also get more extreme rainfalls as well. So then what I tried to do is to look at the average of all the sites where we have rain gauge data, and that is a black curve here. Sorry, black curve here. So that is based on the available data, which is the map with red dots here shows where the available data is. But then in some places the rain gauge data is sort of finished long time ago, and sometimes it didn't start until quite recently. So we have like an uneven sample. So if you see this lower curve here, the black curve shows how many rain gauge records we have. So between 1950 and 1980, we had like a fixed sample of rain gauge data. But before that, you had much fewer data. So then you can't really trust the statistics. So then I thought, okay, what if we say that the mean intensity average over all stations is a result of the global mean temperature? And then we tested that with a regression analysis, and we got a quite good fit, and then we can use that to actually estimate before and after. So there's a lot of uncertainty in this figure, but what it seems to show is that the mean intensity is increasing over time as well, and that's of course that is sort of consistent with also like a declining area. So then I thought, okay, what can this be explained in terms of changed cloud climate? We get different types of clouds. So how can I check that? So I want to. My hunch is that if you get more convective clouds, like the thunder clouds, you get more intense rainfalls. So to do that, to see if that can be the explanation, I looked at the winds going up and down in the atmosphere, and this curve shows basically the convective activity in different parts of the atmosphere. So the blue one is the upper part of the atmosphere, and the dark blue one is like a lower part, and then the black one is actually in the middle part of the atmosphere. And there seems to be some indication that you get some more convective activity. So that actually is also consistent with, like, you get more sort of taller clouds, but they're not as spatially extensive, and that also can maybe explain why you get reduced area of rainfall and also more intensive rainfall. So to summarize, there are 3 at least explanations for more extreme rains, and one is the increased evaporation and vapor concentration. That is sort of the obvious explanation. And then the other one is the higher clouds. And then the third one is like we have a smaller rainfall area. So then the rains are concentrated over a smaller area. And then also we see that you have more atmospheric overturning, and then that implies a changed cloud climate. The implication for that is actually quite profound. As I said, more floods and more droughts with smaller rainfall area. And I would also say that the global rainfall area is actually a very important additional indicator of climate change, as in addition to atmospheric overturning and precipitation area. So I would thank you for your attention. And now, and here's also reference to the paper, so you can actually use this QR